Molarity. Molarity is the number of moles of solute per dm cube or liter of a solution. Its unit is mole per dm cube and it can be determined with the following formulae. 1. Concentration molarity is equal to 1000 times reacting mass over volume times molar mass. This formula becomes applicable when the volume is given in cm cube. 2. Concentration of molarity is equal to mass over volume times molar mass. This formula becomes applicable when the volume is given in dm cube. 3. For acid-base titrations or reactions, Ca times Va divided by Cb times Vb is equal to Na divided by Nb, where Ca is equal to concentration of acid given, Cb is equal to the concentration of base given, Va is equal to the volume of acid given, Vb is equal to the volume base given, Na is equal to the number of moles of acid reacting, and finally Nb is equal to the number of moles of base reacting. Let's put these formulas into practice by solving some questions. Let's take our first example. Assuming CaCO3 or calcium triiodocarbonate 4 is soluble in water, what is the concentration in mole per dm cube of the resulting solution when 6 grams of CaCO3 is dissolved in water to form 300 cm cube of solution? To determine the formula to use, in our solution, let's write out our parameters. The reacting mass given in the question is 6 grams. The volume is 300 cm cube. The concentration is what we are asked to look for. And also the molar mass of CaCO3 calculating is calcium 40 plus carbon 12 plus 3 moles of oxygen plus 3 atoms of oxygen, that is 16 times 3. Adding up this, we have 100 grams as the molar mass of CaCO3. So based on our parameters, we see that the formula we shall apply is C is equal to 1000 times reacting mass over volume times molar mass. And so we have C is equal to 1000 times 6 over 300 times 100. Solving mathematically, concentration becomes equal to 0.2 mole per dm cube. It's quite easy and straightforward, right? Now let's take another example. 2. 25 cm cube of a 0.0125 molar solution of Na2CO3 was completely neutralized by 21.5 cm cube of HCl according to the equation below. In the equation, we can see that 2 HCl reacted with just 1 mole of Na2CO3 to give 2 moles of NaCl and also 1 mole of water and 1 mole of CO2. Calculate the molarity of the solution of hydrochloric acid. Our solution is this. As you can see, this question involves a reaction between an acid and a base, so we use the third equation of formula above. Writing out our parameters, we have volume of acid equals 21.5 cm cube. Volume of base is equal to 25 cm cube. Concentration of base is equal to 0.0125 molar. Concentration of acid is what we are asked to look for, it is the unknown. Number of moles of acid is equal to 2 and number of moles of base is equal to 1. Applying a formula, we have CaVa divided by CbVb is equal to Na divided by Nb. Making concentration of acid the subject of formulae, we have that concentration of acid mathematically becomes equal to concentration of base times volume of base times number of moles of acid over volume of acid times number of moles of base. So imputing our parameters, we have that concentration of acid is equal to 0.0125 times 25 or times 25 times 2 divided by 21.5 times the number of moles of base, which is 1. Solving mathematically, we arrive at the concentration of the acid being equal to 0.029 moles per dm cube. Please, students, I want you to practice more stoichiometry questions at the end of this exercise so that you will become very familiar with these sort of questions, especially under molarity, and it will not pose any problem to you in your JAM examination. Moreover, to get summarized PDF notes and questions, you can visit our website www.cognitive.com. Now, to round up this lesson in molarity, I would like to differentiate polymorphism from allotropy. These are two concepts commonly misconstrued by students. Polymorphism refers to the existence of various forms of a substance in the same physical state. These substances could be a compound such as silica, which has three crystalline forms called quartz, tridymite, and cristobalite. These are described as the polymorphs of silica. On the other hand, allotropy is the ability of an element to exist in two or more different forms in the same physical state. For example, sulfur has two allotropes, rhombic and monoclinic sulfur. Carbon has several allotropes such as diamond, graphite, charcoal, and many others. Moreover, under allotropy we have two types, and they are monotropy and enantiotropy. Monotropes are allotropes that cannot change into each other. For example, there is no way that graphite can change into diamond or diamond into graphite. If not, we would all have been very rich. Enantiotropes are allotropes that can change into each other at a particular transition temperature. Tin exhibits enantiotropy because at the transition temperature of 13.2 degrees, white tin will become grey tin. Also, sulfur exhibits enantiotropy. The reason is because rhombic and monoclinic sulfur can change into each other at the transition temperature of 96 degrees Celsius. So, they exhibit a special type of allotropy called enantiotropy.